Hello, everybody. Today's lecture is going to be part 2 on wiring methods. Most of this lecture is going to focus on conduit sizing based on conductors, or how many conductors can we fit in a raceway. If you're unfamiliar with what a raceway is or the types of raceways, your module has a lot of really good diagrams and pictures, or if you find yourself about in the world, look around for raceways. If you're in a commercial building with an open ceiling, you may be able to see these, silvery looking pipes that are going to square boxes. That's probably EMT. Usually that's what you run inside in a commercial building. Outside of your house or your apartment complex, you might see large plastic pipes that go to meters. That would be PVC. So look around, there's raceways everywhere. Now, one thing that I will not disagree with, but just kind of point out, and if you've installed raceways, you'll know exactly what I'm talking about. But the code allows up to, and not more than, 360 degrees of bends in conduit and tubing. So 90, 90, 90, 90 would equal 360 degrees, or 390s and two 45-degree offsets. Now, I'm going to say for both of these runs, from personal experience and struggles, there should definitely be a box midway through for both. You don't have to. It would be exceeding code. Maybe you also take these down from 45 degrees, do 10 degrees, spaced a bit farther apart. But anyway, how you bend conduit and tubing is basically field knowledge. So when you get the chance, make sure you learn. It's a very useful skill. But I just kind of wanted to point out that's gonna suck to pull through. That's gonna be no fun at all. So that's just kind of my 2 cents, I suppose. So 12900 is going to talk about raceways in general. Now, section 12 is a general section of the code book, but section 12 is the only one that deals with raceways in this way. Other sections have rules and types of raceways, maybe, of what to use, but section 12 is how we're going to figure out how many bends can be in a run of raceway, or where we're required to have our supports, or the distance between those supports, those kind of things. In general, we're going to pull in individual conductors, or maybe some control cables or data cables, but we're not usually going to pull armored cable into a raceway, or NMD, or non-metallic sheathed cable, into a raceway. We might at times to give them some extra protection, because a raceway's has more structural integrity, let's say, than AC90 or NMD90. And moving on and just looking at a couple of the specific rules in 12900. 12906 is telling us that we have to basically have a bushing or something that will protect a conductor that's 8 gauge or larger. You could also look at, you don't need the bushing for anything smaller than a number 8 gauge. That's sometimes the 2 ways I like to read things in the code book to help my brain process this wealth of data and information. You can't have more than 200 conductors in a single conduit or tubing. I don't know when the hell you get to that number, but it's there. You can't have more than 200, so you can't have 201 or more, because you shall not exceed 200 is the wording there for that rule. And then skipping over that main rule we're going to look at for a second. The stranding of conductors, 12914. So a number 8 gauge or an 8 gauge, kind of sounds more proper to me, but anyway, 8 gauge or larger, copper or aluminum, shall be stranded. So that 8 gauge wire, the number 8 wire, when we're putting it in a raceway, that seems to be the benchmark for when we're going to think about it differently. So that could be because 14104 has us having a 10, 12, and 14 gauge at their specific ampacities. So maybe the code book is taking that into account. I don't really know. Just know that if you have an 8 gauge solid conductor, that can't go in a raceway, which is somewhat to our benefit. I don't want to pull, like if that was a number 4 solid, I don't want to pull that in a raceway. That's going to be a pain. I don't even know who has that. I don't know why they have it, but get it out of here. I don't want to deal with that large solid wire. That's a pain. A number 8 gauge that is solid that we do install, for example, would be the cable for your range is usually an 8-3. So it would be 8 gauge 3 conductor. And we talked about that in the branch circuits lecture. But the main one I want to look at today, the thing that most people seem to struggle with, is conduit sizing or conduit fill, or how many wires in a pipe. Is another way to phrase it. In 12910, I'm on page 133, subrule 4 has some specific information and some tables that apply to sizing conduit or figuring out, hey, I have these conductors. Can they all fit in this conduit I have? Do I need a bigger one? Can I use a smaller one? Those kind of things. I'm primarily going to be using table 6 or 6A to 6K to figure out my cross-sectional areas of insulated single conductors. Table 10A to 10D is close to the same thing as table 6's, as the table 6's. Table 10 just has individual conductors, and that'll make a bit more sense when we go and look at these tables. And table 9's, or table 9A to 9H, is going to give us the raceway sizes or their area. So we're going to look at the area inside the raceway because the conductors are going to go in the raceway. So the area of the raceway, the internal area, that is, the internal area of the raceway is going to be directly related to the area of the conductors. Might seem a little bit of a redundant thing to say, but it'll make more sense as we look at these tables. And then table 8 is going to give us what you might call a percentage fill of the raceway, of the conduit or tubing. Back to that example I started with of EMT that you run, sometimes you run it inside in a commercial building. EMT is electrical metallic tubing, whereas PVC is, I can't remember the exact acronym, but it's a conduit. So those are sort of the differences. Both are raceways though. So let's check out these tables. So here is my table 6A. Big, bright, beautiful. I did not do this highlighting on every single one of my table 6's, but if it helps you, and obviously this is the most popular type of conductor I came across, so I highlighted it to make it easier for myself. Versus, let's just for a comparison, there's a lot of data in these table 6's. So to make it easier on myself, I did some extra highlighting. But how the table 6's work is, as usual in the tables, they reference this rule, and it even talks about that Appendix B. So if you look at 12910, it'll say in brackets at the end, Appendix B. We have types of insulation on the conductors. So table 6A is going to give you the area and diameter, but we care more about the area. It's going to give you the area of R90 XLPE, RW75 XLPE, RW90 XLPE, unjacketed 600 volt conductors. And so that's the type of insulation that's on these conductors. And then it's going to break it down into our different sizes. In this first column, we have our variety of sizes of these types of insulated conductors. And so we go from 14 gauge down to 600 kc mil, and then there's more on the other side. This first column here is giving me area and diameter. Now, I care more about the area for these questions we're going to be doing here. I care more about the area of the conductor. So diameter is nice, sure, it's there if I need it. That's swell. But we're going to be dealing with area because we want to know how many of these, for example, R90 might be another way might be the other word they use for these types of wires. Sometimes they drop the XLPE. So I'm trying to figure out how many 14 gauge RW90 conductors fit in a certain size and type of conduit. So this gives me the area of one of these conductors, and then all of these other columns are a certain number of that size and type of conductor. So it gives me the area of one, and then obviously the next column over is for one conductor. So obviously that number is going to be the same, and then it goes 2 conductors, 3 conductors, so on and so forth. At 10 conductors, it starts going up by tens, so then it gives you 20 conductors, 30, 40, etc. So there's 2 ways to go about this. You can either take the 1 and times it by how many conductors you have to get you the area. Or, let's say, for example, it said, I have 20, what's the area of 22 14 gauge RW90 conductors? Well, I take my ruler because you might be able to tell already, that makes it a lot easier to stay with the conductor I'm dealing with versus just trying to follow my finger across, and maybe my finger goes down and up, who knows. So I put a ruler just like that, and maybe I even take a second pen or something and stop myself at the 20. And so I gave myself 21 or 23, or sure, let's say 23 14 gauge. So I take this number from the 20 column, 177.34, and I just add the 3 column to it, 26.6, and that would give me the area of 23 14 gauge RW90 conductors. Now, we'll look at table 10 as well briefly. I'll just say, in case anyone comes across this, there is a slight difference, very slight, but basically it's usually 0.01 millimeters squared difference between taking one conductor and multiplying it instead of taking a number and basically adding the areas. It's probably just due to some kind of rounding that they did or didn't do for table 6s. And so if you're a paranoid person and want to be extra sure that you get the precise right answer, you can just add up the different columns to get your desired number. That's fine. I'm probably just going to multiply by the 1. I've never seen that lead me astray. And in general, in the field, since you want to leave room in your raceway for basically pulling in extra conductors after the fact, if you filled a conduit up as much as you could based on code, you would probably then upsize that conduit because you want to leave room for, one way you could call it, you want to leave room for the oh shit factor, which is, oh shit, I forgot an extra wire. Oh shit, there's 2 more circuits over there, and now our conduit's undersized. So that's kind of what you do in the field, but in code class, we're going to do the minimum sized raceway for the conductors that we have. So in code class, we do everything to the minimum that code requires, except for our overcurrents, which we do the maximum based on the conductor, based on the wire. So with all that said, there's multiple table 6s, and they each have their own type of insulation, and we'll look at a couple of those with our questions. But after table 6s, they have this table 7, which is just the radius of conduit or tubing bends. Okay, swell. I'm not too worried about that right now. Table 8 gives you the maximum allowable percent conduit and tubing fill. So, if we only have one insulated conductor or multi-conductor cable, which is not lead sheathed, we can fill up that raceway, or let's just start saying conduit and tubing. And if I say conduit or tubing, I'm probably talking about both, unless I'm talking about a specific one. So table 8 says if you have one insulated conductor that's not lead sheathed, you can fill up that conduit to 53% of its total area. Apologies for that. So where were we? So we were talking about 53% fill of the conduit, or the raceway, or the tubing. If we have 2 insulated conductors, we can only fill that raceway to 31%. If we have 3, 4, or more, we can fill it up to 40%. So, and that's all for not lead sheathed. If we had a lead sheathed single conductor or multi-conductor cable, our fills are different, because basically you're gonna take that size from table 6s or table 10s, but then it has a lead sheath over top of that insulation, so it's gonna take up a bit more room. Now, if there's 3, I guess the code book's saying, yeah, that room is not such a big deal, but more than that, it's gonna say 35% fill. So that's basically table 8. So here we are on table 9. And how the table 9s work is we have basically pretty much all of our general types of raceways. On the other side here, we have 9B, which has some more specific types. Okay, but 9A and 9B, for that fact, are giving us 100% of the area of these sizes of raceways. Or for this column, it's giving us the area, 100% of the area of rigid metal conduit, the internal diameter and cross-sectional areas, the internal area of rigid metal conduit at 100%, when its trade size conduit 21 is 354 millimeters squared. Okay, so table 8 gave us a percentage fill. We never fill the conduit to 100%, but table 9 gives us those areas should we need it. The table that we deal with the most, or most commonly I'll say, because usually we have 3 or more conductors in a conduit or tubing. There's not much point to put up a piece of 3/4 EMT just for one wire. I mean, if that's what's needed, that's what's needed, but usually we have multiple wires in a raceway. If you're going to go to that effort, you're going to put as many conductors in there that you can. And so I used to say this is the default it's not exactly the default. It kind of functions like the default because most of the time we're dealing with not lead sheathed, 40% raceway fill. So table 9G saves us the step of multiplying table 9A by 40%, and it just gives us the area of, this time let's look at electrical metallic tubing. I'm going to get my ruler out because that's far away from the trade size conduits. And so it gives us, for trade size conduit 21, if it's EMT, electrical metallic tubing, 40% of the area of that trade size is 132.03 millimeters squared. So that saves us a step as we're solving these questions. And sorry if I didn't show that on the camera, but you can see it in your own code books. It also has PVC in here. We got flexible metal conduit. We have liquid tight, flexible conduit, EB1, which is basically EB is a type of plastic piping. EB is, I believe that's encased burial. And then DB is direct burial. So, but the question will just give you those acronyms. You don't have to memorize what those mean. And so just like when we did section 4 and we had to deal with tables 1, 2, 3, 4 and the multiple table 5s, these tables you'll get better with when you practice. So I designed a couple practice questions. I made the question, the color of the font for the question, this kind of sun color, because if you start your day with a code question, then your day will start bright and sunny and warm and happy, because a day without code is a day without sunshine. So let's start our day off right here. Let's do a code question. It's like the bright warm sun in the sky. And we'll just start piecing together and pulling information from. This is not a very tricky worded question. Sometimes you'll get questions that are worded to trick you. Just focus on the information. Focus on how it's related to the codebook. Try to find all the places in the codebook that relate. And solve the question without, trying not to stress. I know that's easier said than done. But all the same, there are 5 8-gauge RW90 XLPE unjacketed 600 volt conductors. Okay, so these are my guys. I got 5 of these. And this is going to tell me which table 6 to use. And we'll check out table 10 in a minute. I know I said I would, so we'll look at that in a minute. So this is what I have. And it's asking if these wires will be run in EMT. Okay, so that tells me what type of raceway, what size is required. And by size, we're not talking in inches. You may still refer to conduit and tubing in terms of inches, ½ inch, 3/4. That's fine, but codebook talks in metric. So trade size conduit is sort of a metric measurement, if you will. Page 37 takes the metric and converts it into imperial. If you're ever wondering what these trade size conduits translate to in terms of inches. And so it's asking me the size of this EMT, and it's telling me that EMT will be used as a bonding means. Now, electrical equipment has to be bonded, so we need some way to bond it. And, junction boxes that have EMT run between them, metal junction boxes, that is, if the EMT is installed correctly, that EMT may count as a bonding means, so we don't have to pull in an extra wire. Now, I don't know that because I don't have all the parameters, but the question told me it is used as a bonding means. Okay, perfect. So I don't have to add a bonding wire. I just have these 5 8-gauge RW90 XLPE unjacketed 600-volt conductors. So I'm going to start with table 6A, and that's going to give me the size of 5 of these 8-gauge. And if you're wondering how I know it's 6A already, mostly from practice, but we just looked at 6A, and it had our W90 XLPE unjacketed 600 volt. Okay, sweet. And I have 5 8-gauge, so I'm going to put my ruler there, because I don't always trust my finger tracing abilities. And I could even put a pen here maybe to direct myself down the column for 5 of those conductors. And I can see right here that 5 8-gauge RW90 XLPE unjacketed 600 volt takes up the area of 140.9 millimeters squared. So I'm going to write that down for myself. So table 6A equals, or gave me, 140.9 millimeters squared. All right. Now I'm going to take, I know there's 5 of them, so with that in mind, I'm going to go over to table 8. And I could also write my table 8 percentage up here and just say, hey, don't forget this percentage fill. Now, I know it'll be 40%, but let's go look and make sure. Let's just check. This is our first question. Let's check and make sure at table 8. And table 8, sure enough, confirmed my suspicions that, I mean, it's going to tell you if it's lead sheathed. Don't assume lead sheathed. This isn't exactly a default area. Maybe the question should have said not lead sheath, but a lead sheath conductor is, in general, depends where you work, but in general, a lead sheath conductor is pretty uncommon. Now, you don't need to memorize these percentage fills, because they're, you'll have your code book with you for exams and TQ. But as you practice, you'll start to remember that 3, 4, or more conductors in a conduit is going to be a 40% fill. So I'm going to go to my question. I'm going to say table 8 equals 40%. And since we already looked at table 9G, I'm going to know that that 40% can take me to table 9G, which is going to give me something. And so with that 140.9 millimeters squared, and with the 40% fill, I find myself in table 9G, and I'm going to look down electrical metallic tubing. I need an area that is big enough to hold all of that area of conductors. And what I mean by that is 74.51 internal area, 40%, of a trade size conduit 16 of EMT would not be big enough for those 5 8-gauge wires. So I'm going to go a size up and see where that takes me. 132.03. Yes, that is big enough. And that is my minimum size, which would be a 21 trade size conduit of EMT. So my answer for this question would be 21 TSC. It's usually the way we write that. Like that. So that's how we solve that question. Our next question gives us a couple different sizes. Okay, I think we can handle this. So we have right here, we have 2 12-gauge. All right. I have 4 10-gauge. Okay, cool. And I have 1 14-gauge, and it's my bonding wire. Okay, so that's going to satisfy my bonding means. That'll keep section 10 happy. We always have to keep section 10 happy. And all of them are solid conductors and are 90 jacketed 600 volt. Okay, well, 12, 10, 14, yep, they can all be solid and in a conduit, so that's no problem. And it's giving me rigid metal conduit and asking me what size of that rigid metal conduit is required. Okay, so first I need to find R90 jacketed, because our last question was unjacketed. I need to find this table 6 that has jacketed R90 600 volt cables. And here we have table 6C. Get this out of the way before I throw that paper around. Table 6C has my R90. It's jacketed. It's 600 volt. Okay, perfect. Table 6C, this is where I'm supposed to be. Sorry for the rhyme there. Table 6C is where I'm supposed to be. Now, it said solid, but these are all stranded. So I'm going to turn the page over to page 431. And at the bottom, it's going to give me solid conductors. And I see I can have 14, 12, and 10. So, I mean, that obviously makes sense based on what we saw in the in 12900. And so I'm just gonna, I know that I have one of each size. So I'm gonna take this 14 gauge. I just need one of them. That's my bonding conductor. And one 14 gauge is 12.01 millimeters squared. And you can't see that on the camera. I'm just writing that on the question. And then I have my 12 gauge. And so there's two ways to do it. I could just take this 2, which I'm going to do for this one. I could take, it has 2, and I'll just maybe put a pen there to make sure. Okay, yeah, 2 12 gauge from table 6C are 29.45 millimeters squared. Then I have 4 10 gauge, and I'm just going to do it a little bit different to show you the other way, but it's pretty straightforward. I'm going to do 4 times 18.63. So I just made myself a little calculation here, because I need to know the area all of these conductors will take up, because they're all going in this rigid metal conduit. And so we can do, on our calculator, 29.45 plus, I'm going to do a bracket because I want to multiply 4 times 18.63, close that bracket, plus 12.01. It's going to give me 115.98 millimeters squared. Now, if you took the area measurement of one 12 gauge and multiplied it by 2, you will probably get 115.99 millimeters squared. Okay? Which is a very minor difference. It shouldn't give me the wrong answer, but I like to stress that difference in case anyone's concerned about it. And so I'm going to take that. I know, since I have 7 conductors, that table 8 is going to give me a 40% conduit fill. You can go to table 8 and check. It's always good to check your answers. Sometimes it's easy to do with code questions, checking your own answers. And so that's going to take me to table 9. Sorry, that's supposed to be an arrow to direct me to, hey, table 8 equals 40%. So that's going to point me to table 9G. Sorry, that's a 6. Table 9G. So let's go to table 9G. So table 9G, right? Got all our 40%. I'm looking under rigid metal conduit because the question said that's what we're going to put these conductors in. Our area is 115.98. Now, just as a side note, just to derail this whole question, diameter 12 is a 3/8. I believe it's a 3/8 conduit, or basically it's going to be either a flexible metal conduit, metallic liquid tight, or non-metallic liquid tight. You can get 3/8 flex. You can only install it in certain ways, and if you look under 12900, it tells you exactly, the length and the application for 12 trade size conduit. Just want to point that out while we're in table 9. Normally our minimum size, except for this column, but normally it's trade size 16 or a 1/2 inch conduit. So 115.98 millimeters squared. A trade size 16 rigid is not going to be big enough. So we go one size up. Oh, look at that. 21 trade size conduit, once again. Can handle 141.6 millimeters squared, and it'll still be just 40%. So we're under that. So our minimum conduit size would be 21. So once again, 21 trade size conduit is our answer for that one. Now, another type of conduit sizing question is or another approach, if we want to think of it that way, is given a size of conductor and maybe a size of conduit, we might be asked how many of those conductors of that size can we fit in a type and size of conduit. So this question gave us, how many 6-gauge RW90 unjacketed 600 volt conductors fit in a 63 trade size conduit of rigid metal. So I'm going to look at this one backwards to how we did the other questions. So with the given conduit size and type of conduit, it gave me a 63 trade size conduit of rigid metal. I'm going to take the area. I'm going to take it from 9G because that's 40% conduit fill. And I'm going to pretty safely assume I can fit 3, 4, or more number 6s in a 63 trade size conduit. So I'm going to write down this number for myself with the assumption that I'm going to fill that conduit to 40%. So that's 1,255.62. Maybe I'll just highlight the conduit like this, direct it to, hey, I got this from table 9G, which gave me 1,255.62 millimeters squared. So that's the area I'm working with. Now I want to know the size of one of these 6-gauge. So I'm going to go to, this looks like it's going to be table 6A, RW90 unjacketed 600 volt. So let's go to table 6A and see if that type of conductor fits. And it does. RW90 unjacketed 600 volt. Okay, cool, super cool. One 6-gauge conductor is 37.94 millimeters squared. So table 6A equals to 37, I believe that was 37, let me make sure here, 37.94 millimeters squared. Now, there's a couple approaches to do. We could just do this mathematically, sort of some ratio math, if you want to think back to that first theory module. But just sort of to make sure I'm going to be in the right range, I know that the most area I could fill is 1,255.62 millimeters squared. That's what's 40% of that conduit. And if I look with these multiples of 10, number 6s, 20, 30, 40, 50, etc., 30 number 6s is 1,138, and 40 is 1,517. So I can already know that my number of 6-gauge conductors is going to be somewhere between 30 and 40. It's not going to be 40. We can do more than 30, but we can't do more than 40. We can't even do 40 because that would be too large for the conduit we're given. So I know it's going to be more than 30. So I could just take this number and keep adding one at a time until I basically go over the allowable area. Excuse me. And then I would just back it off one. Or I could just do this sort of ratio type of math. And what I mean by that is I'm going to take this number and see how many times it goes into this number. And when I say it like that, how many times does this number go into that number? We're talking about division. So 1,255.62 divided by 37.94 millimeters squared is going to give me, we'll just show that on the camera, on the calculator, 1,255.62 divided by 37.94 gives me 33.094 blah blah blah. So I'm going to say 33.1 conductors, basically. But we don't pull in 0.1 of a conductor. I don't even know what that would look like. So we round down to 33, and that is our total number of conductors. That's how many number 6 RW90 unjacketed 600 volt conductors we can fit in a 63 trade size conduit of rigid metal. So that's a different type of question. Kind of the same idea, but we're gonna flip the process and we're gonna do it a different way. Now let's do one more question. I don't know if you'll come across a question like this, but in case you ever get some kind of brutal question, either on the TQ or otherwise, I want to make sure I don't leave you out to dry, because this is a tricky question and it has a few tricks in it because it's tricky. Anyway, so I'm going to start off as I normally do. I'm going to identify, okay, I have 2 of these 250 kc mil RPVU 90 jacketed 1000 volt conductors. All right. And they're with a lead sheath. Okay. So that might affect table 8 maybe. And it says if these conductors will be run in PVC, what size is required? So you might think, okay, I'll go to whatever table 6 table has these wires. But we need to stop for a second and think about section 10. We must always keep section 10 happy. What is my bonding means here? Because it doesn't actually have something that would satisfy my bonding means. Because it's PVC, that's plastic. So that's not my bonding means. So let's jump to 12,900 and see what, or not 12,900, but section 12. Let's look at PVC and let's see what it says about a bonding means, because that raceway ain't gonna cut it. So in section 12 here, page 136, starts us down rigid PVC conduit. All right. And I'm looking over for this word, provision for bonding continuity. And it's going to say that a separate bonding conductor shall be installed in a rigid PVC conduit in compliance with Rule 10614. Now, notwithstanding sub-rule 1, so forget everything you just read. where a rigid PVC conduit is used as a consumer service raceway between the service head and the meter mounting device or service box, a separate bonding conductor shall not be required unless specifically mandated in other sections of this code. So if you remember back to our service requirements, we were talking about running a USB cable underground, and then it would come up from the earth into the meter base through a PVC conduit. So in that case, we didn't need a bond, right? We had our two live wires, and those had a concentric neutral around it, and that satisfied our service requirements. But this question did not say it's a service. We can't assume that it's a service, so we need to keep section 10 happy. So let's go jump back to section 10 and see what this is all about. So I don't know if this is a typo or not, but that 10614 we just saw, under provisions for bonding for PVC conduit, 10614 does talk about a bonding conductor, but maybe it's just the requirements. I'm not entirely sure, but what we're actually going to use is 10616, because we know we need a bonding conductor, but we don't know what size. Now, it's not a grounding conductor, to which I would probably say, hey, do a number 6, copper. You know, that's a pretty safe bet for the grounding conductor. But we're talking about bonding. And we're talking about putting that bonding conductor in the raceway. And so 10616 tells me the size of a field installed bonding conductor. Sweet. That's what we're doing. We're field installing a bonding conductor. Install it other than service equipment. Yep, that's us. Shall not be less than that determined in accordance with Table 16 based on A or B. Now I'm going to save us some time and say that B does not qualify us in this situation because it's talking about volt drop, which is a different lecture altogether. So A tells me that the ampere rating or setting of the overcurrent device protecting the ungrounded conductors. And so that's what I'm going to base my Table 16 field installed bonding conductor on. It's going to be based on the ampere rating or setting of the overcurrent device protecting the ungrounded conductors. So now I need to size an overcurrent to figure out what size my bonding conductor is. Now we know it's a 250 kc mil. We're going to say that everything's 90 degrees Celsius rated, just for the sake of this question, for the sake of argument. So I'm going to jump to table 2 because I know I have conductors in a raceway. Nothing told me that those 250 kc mil are aluminum, so safe to assume copper, which is our default. And I'm going to use my handy dandy ruler once again. 250 kc mil. The 90 degree column is good for 290 amps. Perfect. So I take that 290 and I go to table 13 to size my overcurrent. So table 13 has, now I know here I wrote to myself, load not given, no table 13, but we're just using a hypothetical situation to figure out how we size our bonding conductor. Excuse me. So 251 to 300 amps ampacity of conductor. Okay. Yep, that's the range I'm in. So my overcurrent is a 300 amp overcurrent. So I'm going to take that 300 over to table 16 based on what 10616 told me. And under table 16, I see not exceeding 300 amps. Okay, that's the range I'm in. I see I need a number 4 copper for my bonding conductor to be pulled into this PVC with my 250 kc mil. So the question didn't give me that number 4, but it also didn't give me a bonding means. So I have to still make this to code, and I'm going to add a bonding conductor. So I'm going to say plus, I'm going to put above here. You can organize it how you will, but just organize your code question math in some way. I'm going to say it's a number 4. And I'm going to say another bracket. Maybe that should be in the same bracket. That's my bond. So that way, at the end of the question, I can see, oh yeah, I satisfied the bonding means. So now I'm going to go find what table 6 table, or which of the table 6 tables, or categories, or columns, whatever, has RPVU 90 jacketed 1000 volt. So I found it on table 6F. And I know I have one number 4. That's my bonding conductor. Okay, so I'm going to write down 103.33 millimeters squared. Perfect. And then I just scroll down. There's my 250. And I'm going to use, use whatever you have available. TQ, you might just have a bunch of pencils, who knows. So I'm going to use the back of my calculator. You also have a calculator on the TQ, so maybe you can use that in the same way. And 250 kc mil, their area is 866. All right. Right on. So those are all the wires that are going to be in this conduit. So I'm just going to add those up, 866. Plus 103.33 is going to equal 969.33 millimeters squared. Right on. Now I'm going to go to table 8 because there's a lead sheath and I'm not very familiar with that. I'm used to non-lead sheathed. So let's go see what table 8 says about these 3. We'll assume this bond is also lead sheathed. Since these other 2 are, we're going to make the bond wire also lead sheathed. And I didn't actually mean to do this for this question. But it gives us a 40% conduit fill. So that's fortunate. Now, if it gave us a 30% conduit fill, I'm going to save you some time and tell you that none of the table 9 tables have a 30% conduit fill table. So what you would do in that situation, if we didn't have the bond, let's say hypothetically it was a rigid metal raceway, and the rigid metal raceway functioned as the bonding means. Let's say we didn't have PVC, and we only had those 2 lead sheathed 250 kc mils, we would take this 30%, go to table 9A, and you would just do 30% of the area of one of these conduits. You might have to try a couple to see which one would fit those conductors, but if you find yourself in that very strange situation that I tried to put myself in, but the bond kind of messed me up, that is how you would use table 9A if you had an odd conduit percentage fill. Now we don't have that, we have 40%. So we know that we can just go to table 9G because we can do 40% conduit fill because of that third bond, or because of that third wire, which satisfies our bonding requirements. We're in PVC. We have 969.33 millimeters squared. Now, don't let yourself get tripped up by EB1 PVC or DB2 ES2 PVC. Those are not what we're talking about. We're talking about just rigid PVC. And I'm looking for someone that'll satisfy 969.33 millimeters squared, whatever the minimum raceway size is. And so I'm sliding down. I'm going farther than before. and it's going to be a 63 trade size conduit, which can handle 1,180.51 millimeters squared. And there we go. So I designed this question for this PVC scenario, or if there's basically any plastic raceway, you're probably going to need to pull in a separate bond. There's also scenarios for EMT where you also have to pull in a separate bond, because if you put it, well, let's just go look at that code real quick. And I kind of cheated for myself to save myself some time, obviously, in my code book. We're under electrical metallic tubing, and these are the ways in which you can use EMT. And if you're wondering about supports, it takes you back to basically the supports for, well, not basically, it does take you back to the supports for rigid metal conduit. And so these are the ways you can use EMT. What I was just talking about for a bonding means is on the next page here, on page 142. It talks about provision for bonding continuity. And it tells me where bonding is required by section 10. Yeah, okay. A separate insulated bonding conductor shall be installed in electrical metallic tubing that is installed in concrete or masonry slabs in contact with the earth, a wet location, or an outdoor location. So if you have EMT basically not in a dry condition, or, if it's in these situations, you have to pull a separate bonding conductor. Now, electrical non-metallic tubing, much like PVC, provision for bonding, a separate bonding conductor shall be installed. So that one's a lot more straightforward. That just says, pull in a bond if you're using this non-metal plastic type of tubing. Now, one last thing to look at is called the coefficient of expansion, I believe. Or expansion and contraction of a conduit. And I want to talk about this one because it's sometimes a pretty simple math problem once you do one of them. And I'm going to highlight Appendix B because I should have done that because that's going to matter. And Appendix B is basically like, hey, I got you covered, because the module doesn't really explain it the way that it would make sense. And I'm going to show you what I mean, because on page 41 of your module, it talks about coefficient of expansion. It does a good job explaining it. However, this math to me does not make sense, because minus 30 plus 30, because it says minus 30 to 30, but that could be misleading a little bit, because it has minus 30 plus 30 would be 0. So just to save any possible confusion on that coefficient of expansion, let's go look at Appendix B, because it has a beautiful explanation of it. So I'm on page, I'm on page 586. I'm in Appendix B, and they have an example of this coefficient of expansion. And it says, the change in millimeters, it gives you sort of an explanation, and it says for a 20-meter run of rigid PVC conduit, and the minimum expected temperature is minus 40, and the maximum expected temperature is 30. So we're basically doing the length of the run of conduit times that difference in temperature. So the difference from minus 40 to 30 to plus 30 is 70. So you just add those two numbers up, and then you times it by this temperature coefficient, or coefficient of linear expansion is actually what the code book calls it, which is on the previous page, 585. So, for example, we have a PVC conduit There's rigid RE conduit. We have steel conduit, which is probably rigid metal conduit, would fall under the steel conduit category. We have aluminum conduit. All right. And you take this number, times it by those other two values, which is once again the length of the run of conduit times your change in temperature times that number from the previous page. And that's going to give you the basically how much that conduit is going to move in that temperature range based on that length of conduit. So I wanted to point out Appendix B. That's a very helpful little example. And that should be the end of part 2.